Yeah, hello, this is Lutz Gross from the University of Queensland, and you might know that I'm connected with AuScope for many, many years now through the AuScope project. I want to talk today about a new technology we want to add to eScript, which is adaptive meshing, and this is work with Zee Lee, who is a PhD student of mine, with Adam Ellery and Andrea Cott. Give you a bit of motivation. So we want to recover a gravity field, let's say, of the Australian continent, and particularly looking at the impact or the contributions of topographic features or potentially water and ocean to the gravity field, ignoring the subsurface anomaly initially. And this is an important question because potentially if you do gravity inversion, you want to correct for topographic features before you do inversion. Or you want to look at mass changes, like in the context of remote sensing, for instance, to monitor changes in the ice sheet. You could, for instance, do with high accuracy gravity recovery. The problem is that the features we're looking at, like mountains, ocean, ice, are very small compared to the extent of the Australian continent. So we're talking about features in the size of a couple of 100 meters to a kilometer, or in that range to an extent of about 5,000 kilometers. So if you look at meshing this in the fine element context or represented on a computer, you get enormous problems because of this scale challenge. So typically how this is done, you use a reference model of the Earth, which is basically flat, has only air and some background gravity density to it, and you subtract this from your features or your real Earth, let's say, and you're ending up with little features like mountain, I can see on the right here, mountains, the ocean, ice sheet, from which we want to recover. Because they have different densities, we want to recover the gravity anomaly these features create. At this point, we want to ignore subsurface densities. That would be part of an inversion process. What we'll use is grid refinement. Here's an example on the right-hand side. So we're using a grid-based refinement strategy where we're basically cutting grid cells into subgrid cells. And in the first step, you would use that strategy to represent geometrical features like the mountains of the ocean. And then in the second step, you want to want to make sure that the gravity we're actually calculating has a high accuracy. That means we need to adjust this mesh not only because of grid geometrical features, but also because of numerical features of the solution. And again, we want to use local refinement strategies rather than global refinement strategies, because local refinement strategies are more cost efficient. If you think about global refinement costs, computer costs are roughly, and there's an optimistic estimate proportion to the third power of the resolution. That means if you halve your resolution, your computational costs will go up by a factor of 8 at least. So the initial grid is basically formed by prior knowledge, which is the topography, and then we want to use solution, calculate solution, or in this case, gravity field. We use that solution then to identify areas where we need to have finer meshes to increase the accuracy, and for that we need an error estimator. There's a few strategies around to do this. One of the classical ones is high order gravity, gradient recovery. And you can also use a Kelly estimator, which is basically looking at jumps in the gradient across interfaces, element interfaces, or there are things called dual estimator. But no one of the details here, but there's a variety of options we have. We normally use a Kelly estimator for this study I'm showing you. So the idea is you can provide an estimation of the discretization error or approximation of each cell. Then you take the maximum, and every cell that has an error, it's let's say in this case 75% larger than the maximum error, you will refine them. Okay, and cut them in half basically, or quarter in 2D. And then need to also look at what we call mesh conformity to ensure that's a rule we apply, that a mesh cell, an edge of a node of an edge cannot have more than one node associated to it. If that situation happens, you have to refine neighboring elements as well till this thing is confirmed. The workflow took basically on prior knowledge, creating an initial mesh from topographic feature, like you see here on the left. We calculated a gradient. We use that gradient to calculate an error estimator. We refine the mesh. We go back to the recalculate the gradient because it was very wrong potentially. So we recalculate that, have another error estimation, refine again, and we loop through this until we are happy with the solution. I'll show you this a little for details of this for gravity recovery we did for North Queensland. That's an area up here near around Cairns. On the right-hand side, you see the bathymetry here. So we're basically dealing with mountains and ocean in this case. And you can see this is the initial mesh we used in 3D. The red area here is the density, is the mountain area. And the right-hand side, the green area here is the ocean part. And you can see the no basement here because it's removed from the reference model. Again, you can see this small ratio between feature height and size of the domain, in particular in the mountain ranges. This is an example of a refinement strategy. So this left-hand side shows you the initial mesh. We use a measure group we use based on the bathymetry and the sea level. And then we start, this is after 15 iteration steps. We end up with this local refinements here. It doesn't look so local in this case. But in reality, you can see that there's a lot of refinements only after 15 steps here. And local refinements are happening in the mountain region and in the water where there are relatively large gradient, so large curvature in the potential. I show you this has had a significant impact on the gravity field recovered. On the left-hand side, you can see the initial gravity recovered from the only by using the geometry. And then after 30 iteration steps, refinement steps, you're ending up with a much smoother gravity. You can see there's some significant changes here in the area in the left bottom corner here, where we see more details coming up and also a much smoother result. You can also see that here in that region in the top, that also gravity is coming in changing and is coming increasing. We can here look at the profile. This is a profile basically in the center of the domain, and the red triangles show you the initial gravity profile, and the blue crosses here is the final gravity that has been recovered. You can see there's significant changes in the range of 50% where you see through this refinement process, which minimizes error. Okay, in summary, this is a refinement history. Let's a quick look at that. You can see the blue line here gives you the number of the error in the with number of cells. So each triangle here is a refinement step. You can see it initially we get a very steep drop in the error, and then it stabilizes itself. The next step here would be probably a global refinement, because if you look at the area, you'll see that it's very homogeneous distributed. If you look at this red line here, this is actually if we would do a global refinement of the initial mesh we use for describing the geometry. And you can see we have done 2 cycles here and that global refinement. So we end up with over 1.5 million cells and an error reduction of not even 50%. And we can achieve the same accuracy with a local refinement with only 100,000 cells. Okay, so you can see how cost effective these local refinement studies are. Okay, so what's the next step for us? So we're working on integrating all this into eScript. So you will be able then to control this workflow, what I did. So initial setup of geometry, grid following geometry, and then the cycle adapting the meshes from Python. And we're working on broadening the application case. So we're going through a lot of unit testing at the moment that are still failing, but we're improving. Well, we're fixing all these things, or like Adam is doing this. And so this will run through the eScript package, and will be distributed the eScript package, which is one of these AuScope infrastructure projects. We hope that that gets available in early 22. Maybe a little optimistic, but in the first half of 22, we hope that we can make this available. And the really goal for us is to bring this whole technology into inversion. So we have done this already for the forward gravity modeling. As you have seen, there's a question now to port that into eScript and in Python. And the next step is then in combining this actually with inversion. And we have started some work or very random inversion, randomized inversion to do this. So we're expecting that this will reduce computational costs for the inversion process, that we can optimize the computational work with lower number of mesh points. We also see that there is a potential that can improve resolution of the inversion result, but this is a bit of a tricky exercise to achieve, but we work on this. So thank you very much.